And today we're going to be hearing from Dr. Yuval Shmilovitz. He did his undergraduate here in geology and history, if I'm correct.
Yeah.
He then went on to do masters and a PhD here in the department. And since 2024, he's been a postdoc in Colorado, and we'll be hearing about his research that he's been doing since then.
Okay. Okay. Thank you, Simon. So hi everybody. I'm very happy to be here. It's been a while. And I want to start, although many of you know me already, I want to start with a big background about myself. So my research goal is to develop knowledge of how climate and geological forcing leads to and encoding landscape changes. And I work on various of spatial and temporal scale. As mentioned, I did my PhD here, and I work on climatic topographic inputs on arid cliff-related hill-slope evolution, while during my PhD I also led other research projects. These extend from modern erosion risk analysis to tackling fundamental questions in desert hydrology and geochronology. And I moved to CU Boulder with the general mission to integrate field perspective and hydroclimate realism into landscape evolution research frameworks. And CU Boulder is actually a very good place to do that, where I'm also integrated within the CSDMS organization. It's a community-oriented organization that's expert in developing numerical models of landscape evolutions. And my two main postdoc projects cover fast-evolving landscape during the Holocene, while also sediment transport in gravel bed rivers. These two will be the focus of the talks today, while I'm also still interested in cascading land surface hazard with some active project that's going on now. My research generally involved measurement in the field and high-resolution terrain analysis. I combine that with hydroclimate realism and spatial temporal data analysis, ultimately to taking these two to develop theory and then implement the theory currently mostly based on numerical implementation. So my goal is to understand better how landscape evolved, and generally landscape on Earth evolved by the competition of two main factors. One is tectonic forcing that create uplift, and the second one is transport of the material from the terrestrial to oceanic and terrestrial basins. And a significant player in this general drama of landscape evolution is one that you all see on your very daily basis, which is simply piles of rock fragments. This sediment heterogeneity affects the landscape evolution by resisting erosion and transport, thus creating topographic relief. While they also, especially on the finer fraction, they control many other near surface envelope of the Earth, such as vegetation growth and infiltration across the biosphere and hydrosphere processes. The challenge of taking into account how sediment grain properties interact with hydroclimate is a long-standing challenge, and this is the focus of the talk today. So this is a challenge in part because this type of science of computational geomorphology is relatively new. It's only 70 years ago since the time-focused approach, evolutionary-based approach, were transformed into more computational approaches, process-oriented. And I summarize from the literature what I understand as the main component of modern geomorphology research, which is based on measurement of the landform, quantification of the external forcing to drive landscape changes, and then ultimately with the goal to form mathematical models that can upscale in time and space. We live in a very exciting area actually this time, because this is the first time we can apply this entire methodology over a wide range of geomorphic processes, domains, time scale, and also regionally. And this is especially because the emergence of capabilities. These days, we can measure near surface properties much in better resolution than before. If in the 80s we can work on measure river profile from space, that only rivers at the scale of the Mississippi River, by the early 2000s, we can work at the scale of rivers that drain the Judea Desert. And these days, actually, we can measure sediment statistics from space. But this is only one side, only one revolution. There is also a very significant revolution on the climate side. These days, climate models reach out to the point where they provide us, geomorphologists, event scale perspective of what drive landscape changes and how the landscape has been changed. And this is not only in the modeling side, also in the observation side. Climate attributes can measure today from space all over the globe. The thing is that bridging these two into the science of surface processes is very much lag behind, and there are many good reasons for that. I want to highlight two of them. One is it's hard with this emergent and boom of measurements. Sometimes we realize that we need to take into account more interaction of across different spheres of the Earth, which also required some advanced physics-based understanding. But also there are challenges in relation to the time scales. With this boom of observation, we now need to find a way to overcome uncertainty, variability, and computational challenges in order to upscale across time and scales. With all these great challenges, there are also opportunities. And so you all probably aware of the possibility to forecast of weather, but did you ever thought about the possibility to forecast landscape changes? And the community recognizes these opportunities, and this is what this term Earthcasting stands for. But not only for this kind of application, it is probably important for policy making. My vision that this kind of revolution could also provide us information of some of the very basic questions in the science of surface processes and terrestrial landscape evolution. For example, we can explore which event dominate surface processes on Earth. It can be either the very catastrophic event or maybe more common events that we can measure, and they also take, they also dominate over geological time. And one of my chapters in my PhD actually kind of scratched the surface about it. But these days we can do much more. And I want to highlight a few fields, and I will end that the introduction with these new open fields. One of them is the relation between material property, hydrometeorology, not necessarily general climate, and topographic imprints. We can study much better now specific climate conditions in relation to landscape and life, trying to understand better what drive environmental crises over the recent geological past, while also focusing on cascading land surface hazards. For example, hazards that involve sediments, as we all observed that happened yesterday. So the talk today is going to focus especially on these first two, and I will present some contributions from my postdoc term. And the first site that I want to share with you today as a natural experiment is the Front Range of Colorado. This amazing site, this cool landform associated with this lithological boundary where there is sedimentary rocks that form the high plains, mainly fine-grained rocks, while the terrain, the mountainous terrain, is associated with much coarser material, metamorphic and crystalline rocks. And we can use this general landscape to ask what is the role of sediment heterogeneity in this general drama of landscape evolution. And I just want to mention that this is not a specific case. We have some very cool examples of rivers that drain different lithology from our very backyard. The challenge is, or the gap is, that we don't actually have a good mathematical model that could represent sediment heterogeneity. What people often use to describe fluvial incision is this kind of simplified stream power law that depends on this erodibility factor that take into account many factors, also including the sediment part. But this kind of relation cannot address spatial and temporal variability of sediment heterogeneity. This is actually kind of a gap, because sediment is one of the most measurable elements of the system that we as geomorphologists measure in the field. So I want to introduce a newly developed integrated theory and implementation in numerical simulation or numerical experiments. And the idea that we try to describe this kind of system, river system that associate with spatial and temporal variability of sediment cover and sediment properties. So the idea is that we describe the change in rock elevation as function of some tectonic forcing, which is create uplift. The plucking process, which is this integration of blocks associated with some fracture spacing, and the process of bedrock abrasion, which is, you can imagine, as a grain by grain erosion of the bed. We're really interested in sediment, so we're going to describe the sediment, how the sediment depth changes through time, and this is affected by the plucking process, which produces sediment to the system as a source term. Attrition, which is the process of sediment breakdown in association with sediment collisions, and obviously the sediment flux from upstream, downstream in the system. So after formulating the theory, what I'm doing is implement that in numerical experiments where I can control different variable and system. For example, here are two landscape evolution, mountainous terrain landscape evolution under two different grain size properties. And the idea that we gonna run these systems up to steady state. That means that uplift is in equilibrium with the entire transport processes, ultimately into reaching a point where the topography represents the processes. And one of the main differences that we found is that grain size affect quite significantly the landscape. So this is river profile, this is distance upstream and elevation, and you can see how significant the river profile change just by sediment, the sediment size. And this is actually significant as this range is conservative. This is range based on measurement that I collected and also from the literature. And we know that on Earth, the sizes are actually, the range of sizes that hillside produce to the fluvial system is actually much greater. It can range across 3 orders of magnitude. This is although the significance of the sediment grain size, they're rarely implemented explicitly in mathematical models. But it's not only the size, also the spatial distribution of grain size matters. And these are two experiments under steady state, where in this case, the upper part of the stream is coarser, produce coarser sediment relative to the downstream part. And you can see that this river profile is very much similar to the case where the entire domain is coarser. And this is because the upstream delivery of coarse material go over the entire profile shape. I want to emphasize that differences in the grain size not always reflect lithology. This is an example from the Negev, where microclimate properties leads to different grain size distribution. So this is not necessarily represent lithology, it can represent differential weathering, for example. The opposite case looks quite different. So under this case, the upper part of the stream is much finer, produce finer material relative to the lower part, and under steady state, the river holds this nick point, or this breaking slope. And we give, as geomorphologists, there is a lot of meaning for this shape. As we teach in Introduction to Geomorphology courses, that this form of rivers represent transient case in response to climate or response to tectonics. This is also shown here in one of the state-of-the-art books that introduce concept in geomorphology. So based on the analysis that I just showed, we might need to update that as also changes in sediment properties, the heterogeneity, could lead to these topographic forms. I want to take one step further and to show you how the 2D spatial patterns of the landscape affected by differential grain sizes. And this is an experiment that is much motivated by the case study in the Front Range. And under this case, you're going to see the landscape evolve over 5 million years with this contrast of grain sizes. And you can easily recognize that just by simply include explicitly the grain sizes, we were able to generate mountainous terrain, while the lower part is very similar to the relief differences of the high plains. But there is also another thing that's interesting here, and it's inversion of topography. Streams that start to evolve at the beginning of the simulation, as you looked at now, act quite weirdly. They become inverse. The topography is inversed. As I summarize in this cross-section here, they just plot the topography across this line for 2 times. This is the beginning of simulation. This is by the end of the simulation. And this inversion of topography is commonly found in the Front Range and other mountain ranges assigned to climate and tectonic forcing or changes, but here we show that it can be merely due to changes in the grain sizes. It's not another significant property of sediment is their hardness. That means how fast a block of sediment breaks into very easily and transportable material. And this could actually take a significant part in the evolution of the drainage, as the drainage received material of different hardness from different places. This is an example from the Front Range, and this is a geological map where you can see there is a heterogeneity in the lithology, in the hardness. But this I want to show another kind of example from rivers in Taiwan, where upstream source of hard material play a critical role in incising into much softer material that is located in the downstream part of the channel. So the idea is to formulate this kind of an experiment of non-local lithological heterogeneity, and I formed these 2 symmetrical catchments that associate with spatial heterogeneity in the very upstream part. At the beginning of the simulation, you might recognize that the drainage divide is symmetrical, but by the end of the simulation, you can appreciate how the system evolved into asymmetrical form, where the sand-rich catchment is expanded on behalf of the other quartzite-rich catchment. And this is also pronounced in the profile, where the upstream sandstone associated with lower slope and less steep than the stream that associated with upstream source of quartzite. So to summarize this part, by explicitly including sediment heterogeneity in the theory of fluvial incision, we were able to provide testable process form relations. And what is also significant is that some of the landscape patterns that we were able to reproduce were commonly discussed for decades in the context of climate and tectonics. But here we show that by the advanced theory, they can result merely due to sediment heterogeneity, something that is rarely explicitly implemented. And there are much more to explore. This is the very beginning of the general project, and we provide these open source modeling tools that people can now use all over the world to test hypotheses in different places across time scales. So far I focus on systems that develop over that extent, over this mountainous terrain, and the next part of the talk will focus on smaller domain. And over this smaller domain, soil-covered, fast-evolving landscape are very sensitive not only to the sediment heterogeneity, but also to climate. And I'm going to try to convince you that we have new methodologies to, for the first time, take this high-resolution climate data set and examine sediment heterogeneity sensitivity to such climatic transitions. And some example of how this landscape looks like on Earth. So this is an example for gully system that developed on the mud plains of the Dead Sea in association with the Dead Sea level drop. this kind of soil covers fast evolving landscape, very common in the southwestern US. They stand essential of environmental disputes. Not only in drylands, this is an example from the French Alps, where these badlands contribute much of sediment and carbon to the Mediterranean Sea. And also, not only on Earth, in other planetary bodies, this system exists and are interesting to study. So the overreaching goal of this project is to take into account this kind of weather phenomena, high resolution, highly variable weather event, and how the interaction of this kind of system with the sediment heterogeneity on the surface control the general landscape evolution. And I'm gonna begin with a storm scale perspective, and I will move on by the end of my talk to a Holocene scale landscape transition under rainfall variability. So I started with gaining field and terrain analysis perspective and collecting observation. So this is a hillshade map from the high plains, when you can appreciate actually how significant the landform varies. For example, in the middle part of the screen, this area, highly dissected area, is expanded and capture more and more area, this asymmetry, and this catchment capture more and more area from the much smoother surface on the side. And we found that what is correlate mostly with these differences in morphology is the soil texture. Generally, sand-rich catchment are associated with increase of topographic slope, and also with pronounced asymmetry with significant gully activity and fluvial activity. What caused this sand-rich catchment to be much more dissected, affect the entire landscape evolution? So, in a sense, one can argue that it's simply the shear resistance. Sand-rich catchment knows to be associated with decreasing of shear resistance, which might increase the erosion potential. However, there are many other good reasons in the contradicting scenarios over the high plains that could lead to opposite trends, such as decrease of runoff generation or decrease of the potential of frost action. To make it a bit more complex, there are other near-surface properties that correlate well with this landscape, and for example, the greenness level. Vegetation cover is generally associated with lower vegetation, sand-rich catchment associated with lower vegetation cover systematically relative to silt and clay-rich catchments. So the goal is, after gaining this entire process-based perspective and observation, is to test it. How we can formulate an experimental environment to test this entire dynamics. So after going up to the field, I collected knowledge about the processes that take action. For example, on this soil profile, there is occasional runoff generation on the top with some vegetation cover. It's also recognized some soil layer, which is a layer with some spatial and temporal variability of grain size. And below it, there is a layer that I call bedrock here, but it's actually very unconsolidated bedrock. It's eroded very easily. And then the idea is to formulate the entire process law that governs this interaction of water, vegetation, and soil, and then implement that into numerical experiments that could resemble many complex dynamics, such as rainfall input that translate into runoff. Runoff can change in time and space and also change its behavior. And then during the storm, we have a spatial and temporal variability of erosion and deposition that take into account a various composition of grain sizes and sediment properties in general. And this is a new approach in the community of landscape evolution, because this hydroclimate is usually neglected, as it's too hard computationally and also because of the uncertainties. But here, I'm going to show some new approach how to overcome these challenges. I want to show you one experiment out of many that deals with vegetation, on the rule of vegetation. So these are two hypothetical catchments. On the right side, the catchment will be vegetated. That means that vegetation grow and decline through the season, and the upper part is going to show the gully profile in the main gully profile in the catchment. So this is the topographic profile. The middle row will show the sediment tilt during the simulation, and this is the entire landscape. Just to mention that the left side is a hypothetical catchment where there is no representation of vegetation at all. So I will just let it run, and you will see immediately that under the vegetated case, there is only one gully developed in the catchment, while under the no-veg case, the entire landform is dissected. You also can recognize that there is an upper preserved area in the gully profile and distinct head cuts relative to the no-veg case where the entire gully profile is eroded. This is obviously reflected in the sediment yield, which are much greater under the no-veg case. So the new approach that we presented could quantify interstorm sediment dynamics, taking into account explicit hydrology and vegetation cover, while also some of these landform patterns can explain the landform asymmetry that we found over large scale over the high plains. So far I talk about spatial differences in this kind of low relief landform, and after gaining this understanding of the processes, I want to move on into temporal changes. And I want to emphasize how dynamic these systems are by simply this topographic map. So over this topographic map, you can easily recognize places with pink colors that are active headcuts and failures, while upstream to this active headcut and failures, there are areas that used to be maybe an active headcuts, but not anymore. In between them, there are areas of alluvial field associated with these flat surfaces. And the trigger for these and similar dynamics go back to the very early geomorphologists, such as J.K. Gilbert, that described it and over very similar regions. And people advocate for many possible triggers, such as climatic changes or changes in land use and anthropogenic activities. Using the new approach that I just showed you, I would like to take the few steps forward and examine quantitatively specific rainfall regime that could or not drive this kind of similar transitions. The first challenge is how we can even represent event scale rainfall forcing over time framework of landscape evolution, which span across events to the Holocene. To bridge this gap, I use a tool which is a stochastic tool and a hydroclimate generator. This tool allows actually to simulate any kind of hydroclimate parameter such as temperature or discharge, but I use it for rainfall. And I use the Yuval distribution to describe this rainfall series that depends on two main parameters, kappa, which is a parameter that controls the tail of the distribution, and lambda that controls the average event. And the idea is to generate a long-term series of rainfall record, very high resolution, let's say 15 minutes, and then separate the series into discrete rainstorms. As I touch the distribution, I can have many types of storm, like short and intense and long, and that associate with lower intensity. And after generating the sequences, I use my landscape evolution framework that represent hydrology, sediment, and topography dynamically, storm after storm. I want to show you one kind of global climate change analysis that explore a parameter space of both lambda and kappa, the two parameters that describe the rainfall distribution. And the idea is that I create this parameter space in a way that I can plot these isoids. So these are lines that represent various of combination of parameters that all share the same annual rainfall. And then for each combination of parameter, I can generate a long-term time series, separate that into rainstorms, and then project sediment yield. And this is the sediment yield map, which show how much mass this specific catchment lost by different combination of parameters. But we can even take it one step further and look how the topography look like as we simulate topography dynamically. So these are various combinations of topography associated with different properties of rainfall distribution. And I want to highlight only two end members here that go along the main diagonal. As a reminder, the diagonal is IES. That means no change in the annual rainfall, but the lower left case associated with the increase of sub-daily variability, which leads to a 3 times increase of erosion relative to the upper right case. In this last part of the talk, I'm going to show you how we can use this new approach to investigate more geographical related climate change hypotheses. And I focus on the high plains as this area is today lies in the climatic boundary zone, assumed to experience in the recent geological past significant climate and environmental changes. And I use the space for time approach, which assumes that I can find an analog for time in space, but instead of just using climate record from different places, I do that over the kappa space, which means the tail property of rainfall. So I collected the nationwide rain gauge data over the entire US, and then these rain gauges are plotted against their kappa that describe the sub-daily storm statistics. I collapse this map view into a 2D parameter space, describe this kappa in the annual rainfall, and now I can plot specific trajectories. For example, this trajectory that people assume that the high plains oscillate between climate that is more similar to southern Canada today. Using the parameter space, I can generate a long-term time series using my hydroclimate generator and then produce 18,000 years of rainfall record at the sub-daily scale that follows the trajectory that I just showed you. And what's interesting about this trajectory is that there is a contradicting trend. So there is increase of variability with lower kappa, but also the annual rainfall is decreasing. While under the low variability phase, higher kappa, the maximal intensities are lower, but the annual rainfall of the region is generally greater. And then we can explore in the numerical experiment platform how the landscape is gonna behave under these kind of oscillations. So this is what I did, and this is the hypothetical catchment that you already saw before. And I'm going to take you now to this 8,000 years of journey to look how the landscape evolved under this specific trajectory of rainfall changes. So at the beginning of the simulation, you can see that significant gullying occurred in the entire catchment, and this is because of the higher maximal intensity is also the initial relief that I started the domain with. While going over 1,000 years more into the low variability phase, you might recognize these purple colors, which indicate about soil accumulation in the entire catchment. With the transition into high variability phase, there is incision of gully activity, especially in the main channel, removal of material, especially from the mainstream, and then the system will oscillate back and forth twice again, similar to what you already saw. I want to summarize that using these snapshots. So this is a snapshot during the simulation, which indicate that we were able, by changing the sub-daily rainfall, we were able to alternate the system between soil accumulation and soil removal phases that were more pronounced in the main gully channel. And this is interesting because it's very similar to patterns that we observed in the field. So these are catchments that you already looked at on the heat shaded map in the very beginning of the talk, but you can easily recognize in this landscape this flat area associated with alluvial field, while beneath them there are active gully activity where there are actually no much of soil cover. And also the head cut already propagate much upwards. So this is, at least based on my knowledge, the first demonstration if we can take that we took Holocene scale sub-daily rainfall record that assigned to specific hypotheses that leads to a pattern that we can actually measure and examine again directly against the simulation as it's a meter scale spatial resolution. And also we provide some numbers on possible changes. So this kappa, we can measure it, and I'm going to show some example under different climatic trajectories. So if so, under future work, we might be able even to inverse the general landscape into potential paleoclimate sub-daily rainfall, if we assume that climate is the main trigger for these transitions. I want to end my talk by talking about the future. So fast I talked about the past. So we can take the same approach as before, space for time, and under a common hypothesis developed by this group in Colombia, the 100 meridian pseudo climate boundary shifting toward the east over the past decades and may be expected to shift even more in the future. Under this trajectory, taking space for time approach, the climate over the high plains gonna look more like what's happened today in the southwestern US. But for future, I take different approach that I want to share with you. I use specifically high-resolution climate model, WRF projections, that provide weather scale information about storms that drive landscape changes in the surface. And this kind of model become more and more available now. But as we advance our numerical experiment to take into account the specific hydrology, and they can communicate with these kind of models. And interestingly, while looking on this specific climate projection under RCP 8.5, the trend of the future is very is contradicting the space for time approach. It leads into an unfamiliar state, at least based on the North America data set, an unfamiliar state in respect to the sub-daily storm statistics and annual rainfall, which means more variable but also drier. This is something that is not really measured today over the North America. What is the reason for that? So I don't have an answer, but I'm sure that many of you are interested in this kind of phenomena, and I will be happy to discuss this very much further. Anyway, I can use this kind of specific CPM projection to project landscape changes. So this is, if we believe the CPM projections, this is a worst case trajectory for water resources, more variable but also drier. Under future conditions, this hypothetical landscape, the gully headcut retreat and sediment yield is 2 times greater than the historical records, and this is also highlighted here by the fast propagation of the gullies under CPM-based future records. So I want to end my talk by going back to the beginning. My goal is to understand better how and develop knowledge about how climate and geology leads to and encoding landscape changes. And I show that by the advanced theory that now takes into account measurable sediment statistics, sediment heterogeneity, and eco-hydrology relation, we were able to produce some form processes relation, and these relations are global. You can use them and test them all over the globe, while also I showed some new approaches and advancement in numerical tools that are able to communicate with high-resolution climate projections and provide specific quantification of landscape transition under various of trajectories. And I hope that these two together will change our understanding of how sediment records and landscape change through space and time, and also advance the knowledge of the very basic origin of topographic forms. Some of my future plans. So this project can go way beyond. We can include more complex and needed interaction with other climate variables such as dust fluxes, biomass including also human activity using, for example, agent-based approaches. And we can use this platform to investigate specific environmental crises that took action during the recent geological past. I'm very interested in the coupling of topography development and climate at the event scale. This is a research frontier, how the landform affect different climatic phenomena, and these feedbacks were rarely explored, if at all. And lastly, some remnants of my PhD that focused on arid cliff system. I'm generally interested in sediment dynamics, complex sediment dynamics, and land surface hazards. Okay, thank you. Be happy to take any questions.
Thank you. Questions? All right.
Hi. Very nice talk. You just mentioned feedback between topography, landscape evolution, and climate. Can you give examples of these two-way?
Yeah. So what has been actually studied is kind of general phenomena, let's say orographic effect, that probably affect, let's say, the annual rainfall and so on. But we know now there are other storm scale or event scale changes, let's say the inverse orographic effect, which means that the increase of maximal intensity for short duration or decrease of maximal intensity for short duration with increase of topography or relief. So these kind of dynamics will definitely be examined using this new approach that I showed. We can couple changes in storm patterns, let's say, or general weather pattern with increase or decrease of relief. Also taking into account directions and moisture source of directions. This is totally open field.
So first of all, it was a great talk, super interesting. And I'm not sure if I understood something I'm trying to wrap my head around. So you have this really cool model of landscape evolution that has all these parameters and stuff. And you predict a bunch of different things based on it, and you show anecdotally how this works in different places. The question is, how do you ask, is this model true? Like, how is it compared to real life? So how good is it? How do you know to believe you or not?
Yeah, that's a fair question. So my answer will go to two parts and actually two strategies of this kind of model validation. We can go all the way into formal calibration and validation approaches. And because I deal explicitly with the hydrology, which is something that is rarely done, at least to my understanding, in this kind of time scales. But as I insist on that, I can actually calibrate the model, for example, to specific rainfall patterns, but also calibrate sediment yield and runoff. I went to one of the most observable catchment all over the world, actually, that have 90 years of sediment data. And as I run the model over storm scale, I can calibrate the model on storm data. This is an example of model performance, runoff, measured runoff and simulated. This is runoff, peak runoff, and sediment. This is commonly done in the hydrology field, but rarely done in my field. So the idea is to get the understanding that the model behaves correctly. It's resemble the measured properties that we already know, and then we find some trust on it. So this is the first and maybe more challenging task to do it. The other one is that I do think it's quite promising is just looking on the landscape. And people usually done it. For example, I showed it in one of the last diagrams that I showed. So we can look a bit better and measure that. Like we have high resolution topography of that. We can see if the model produced, for example, correct drainage densities, correct relief, correct differences in depth of soil cover, and so on. And this is what people usually do over the very long time scales.
Right.
You're talking about forecasting future evolution of the surface. So how far your models can go? So what are the timescales that you want to predict? And are you looking at slow processes like the one that you showed, or catastrophic ones like flood and
Yeah.
things like that?
Yeah, no, thanks. It's also a very good point. So, so far I focused on Holocene. Like I was able to reach up to Holocene scale at the sub-daily scale, and like this is not arbitrary. This series is of rainfall at the sub-daily scale follows a specific trajectory that people suggested. So going up to the 18,000 years is something that I'm able to do now, and this is with explicit hydrology, as I mentioned. So this is the focus of the very future steps of this specific project. Over the very long term, let's say deep into the geological time, we need to find better ways to do it. We have many ideas. These ideas spread from the specific numerical implementation. I can go into details onto that, but also different approaches. For example, take into account only specific events, as you mentioned, like the very catastrophic one, or not. But yeah, method need to be developed into order to get into the very geological time. So far, we were able to produce that over Holocene scale.
Any more questions? Oh, yeah.
Me again. I'm just wondering about the statistical significance of some of these results. It seems to me that many of these processes would have like bifurcations.
Yeah.
That for some stochastic reason it could go in one way and then just get enhanced. So how do you validate statistically the results of the models? Because again, you seem like very chaotic in some.
Yeah, no, that's definitely happened. So usually we, let's say over the second project that I presented, we explore parameter space and we explore sensitivities in many ways. I don't have a specific figure to show, but maybe I do. No, maybe I have only this kind. So we have complex sensitivity analysis that take into account various of interactions. Mostly we were able, based on field observation, to constrain the interaction to variable, like to combinations that we feel that are more relevant, but we expand them. So we try many types of configurations, and this is what we do mostly for, in this approach that represent the hydraulic realistically, which is based on many parameters. For the landscape scale or the mountain range scales, this is actually a model that is not heavily parameterized. The physics is very simplified as we run it over a geological time. So actually there is no much parameters, and we set it at the beginning with some initial conditions that resemble measured landscape or initial condition that we wish to explore. I hope that I answered.
I was actually asking more about the initial condition, because you could have like a bifurcation at the very beginning. I mean, if you just change the initial conditions just a bit,
Okay.
you could have, landscape developing and maybe some different things. So just the sensitivity, it seems like that would be like a sensitivity.
Yeah. Okay, so about the initial conditions, for the landform, for the geological time, mountain range scales, usually it started with some random noise, and we don't explore many configuration of changes. Only when we have some good reason to do that, as I mentioned, let's say the case study from the high plains, where we produce some, let's say, contrast in sediment properties and so on. For the catchment case, it's actually not very sensitive to the initial condition, as it's associated with base level lowering. So we assume the catchment is kind of smooth at the beginning, and then everything, all the action takes because of the base level lowering rate. So we initiate the surface as flat with some random noise, but it's quite not significant, and because there is only one outlet here that associates with the level of the, let's say, a big stream that runs here on the bottom. So it's not very sensitive to the random noise, and it's flat at the beginning, so it's not very complex. But we can explore many other geometries if we have some good reason to do it.
Okay, I have a quick question. So if you go from one regime to another in terms of climate, so you've got one kind of statistical regime and you move into another one, how quickly, or what kind of timescales are you going to see a response? Maybe I missed this when you talked about this. But what are the timescales that we're talking about to actually see a visible, measurable response in the field?
So it was a challenge, of course, if I understand correctly, you actually asked about this oscillation. Like, how do you find this range of oscillation? Like, they can be really rapid, and then you might not see any change, or they can be longer.
Right, I'm saying, what are the timescales that you would see if you had that kind of pattern? What are the timescales of the response?
Yeah, so I did not examine it deeply enough what exactly is this oscillation range of climate that will produce the landform. Maybe it's also related to Ori's question. So this is very much based on observation and the previous hypothesis. We need to pick something and we try to be as much realistic as we can. Further work could definitely, and I think I did it in one of the PhD on different system, we can examine what exactly is the interval of this change that could produce the landscape that we see or not. But yeah, this is based on observation and previous hypothesis.
So I suppose what I'm really asking is now we're moving into a different regime because of climate change. So what are the timescales? How quickly would we expect to see some kind of response in the landscape? So if specifically regarding the future projection based on the CPM that I'm using, it's happened quite fast. Like you maybe have the figure of the sediment. Oh, I took it out. It's happened quite fast. I need to find this figure, but you don't need much more than few storms in order to start, let's say in terms of the sedimented, to diverge from what the historical record showed. It's happened quite fast. Yeah. And like the last simulation that I showed is 1,000 of years experiments, but you might be able to, so this is, I think it's 200 years interval in the profile, so you can see that already after 2,000 years, the head cuts here is around 110 upstream, and this is like, I don't know, 80 or 90. So it's happened fast, like a few decades or so, the change, at least based on this projection, happened fast. Any more questions?
Just one small question. So just trying to take this further. If you could do this on a large scale, you could take the DM of Earth and say what is the age of every geomorphic spot on Earth, in a sense, right? If you know something about lithology and rainfall, you can make an age map of Earth's surface or age map of Mars' surface. Right?
Yeah, the problem is always the external forcing, because some of this landform, so this evolved fast. This is why I went through them to apply the new methodologies, because we almost can see the change. Let's say the Dead Sea, or this fast evolving catchment in the high plains. We can even use imagery sometimes to examine specific hypotheses. But some other landform, they change through geological time, and we need to overcome the variability and the uncertainty of how climate change. That could lead to to divergence of morphologies, right? But process-based relation, actually, what drives the modern geomorphology is a key, because although many of the systems don't reach steady state, they are close to it. Often very fast, because whenever change occurs, mostly the geomorphic system adjusts fast, and then it's in the way to reach into the steady state. So using process-based approach that are not based on time, that are shown in the very beginning, that often computational geomorphology used as metric of the landscape, could provide